Hello everyone. In this video, we are going to discuss about areas between curves. So basically, we have learned in the previous lecture that we can count areas that is being bounded by the curves from the top and then from the x-axis from below. If you still remember the concept, okay, even though we are talking about areas under the curve, but basically the general idea is we are measuring the area that is being bounded by the curve from the top and then by the x-axis from below. So basically x-axis, if you try to replace it in terms of function, a constant function, you will have it to be y equal to 0. Right, so that's the general version of area under the curve that we have gone through previously, right? But now we want to extend the idea a little bit more, okay? That is rather than having y equal to 0 or the x-axis as the bound from below, okay? Now we are going to have curve as well, okay? From the top, we already have the curve as what we did earlier, the previous lecture. But now, okay, we are adding an extension, okay, to make it more general. Rather than considering y equal to 0, now we are considering a function or another curve, okay, to bound the area from below, right? So that's the idea that we have. Now we want to extend here from what we have learned previously. So there's, for me, there's no new things that you are going to learn basically, okay, in concept, okay, but rather an extension of what we have learned previously. All right, so this is the region that I talked just now. So rather than having the x-axis, now we can see the area that we are considering, the S here in this figure, technically, okay, being bounded on top by one curve, y equal to fx, and from below by another curve, in this case, y equal to gx. So you can see from the statement that we have here, we are considering the region S, okay, being bounded by y equal to fx and y equal to gx from top and from bottom, okay, respectively. And of course, we still need to have the lower bound and upper bound of our integration. That means we are going to have two vertical lines, okay, A and B. In this case, we make it general, x equal to A and x equal to B, and they will be our bound, okay, our limit for integration. And of course, there are things that you need to consider as well. That is, f and g are continuous function. Okay, if you don't remember, you go back to the definition of integrable function. All right, and we have in this case uh, to start with, okay, this particular topic is that we have one specific case, that is fx must be always greater than or equal to gx. Okay, but later on we are going to make it general as well, that there are possibility that some parts of the interval fx is greater than gx, but another part of the interval gx greater than or equal to fx, right? But we start with something small, that is fx, only the case of fx greater than or equal to gx for all x in a, b. All right, so the thing that we are going to do is the same thing. If previously we tried to construct the rectangle, okay, that starts with y equal to 0. Okay, so the x-axis is y equal to 0, right? So if previously we have something like that, so what we did was, okay, when we tried to approximate the area under the curve, is that we construct a lot of rectangles that the base start from the x-axis, that is y equal to 0. So there are a lot of things that we did, overestimation, underestimation, and things like that. But now we extend it a bit more. Rather than stopping at the x-axis, now the height of the rectangle is being bounded by, of course, the top curve and the bottom curve. Okay, as you can see here, the blue one is the bottom curve, that is gx, right? So we want to find the, okay, in order to calculate the area of the rectangle, two things that we need. The first is the base. Okay, we use the same thing here, equal base delta x. Okay, but now the height is taken from the height of the first curve, okay, at minus the height of the second curve. So this is general because you can have, the gx here is not a positive. In some parts, there is not a positive curve. But what matter to us for now is that fx is greater than or equal to gx. So gx can be negative. So in this case, where gx give us negative value, so we need to take the first part, that is from fx, the height of fx starting from the x-axis or y equal to 0 until the top here. All right, from here to here, and then we need to add from here until here for gx. And notice that here we put negative gx, okay, because it is a negative function. So when you try to calculate in usual way, finding the value of gx by substituting the value of x, you are going to get the negative value of the function. That's why we have negative here. So by taking fxi star, xi here is sort of sample point. Okay, you can choose the midpoint or the left point or the right point. Then you minus gxi asterisk as well, right? And then you are going to get the height of the rectangle. Now that we are equipped with the height of the rectangle and the base delta x, okay, using those two, we can calculate the area of this sub-rectangle, okay, within this delta x interval. All right, and then we repeat the same process for every single part between A to B. So we get the figure 2B here. Okay, that is what we call as the approximating rectangles. Okay, by combining the idea that we have from figure A here, okay, and then we have some more rectangles depending on the number of rectangle that we want, the n, right? Then we are going to get the approximation for the whole area that is being bounded from top by curve or function fx, and then from below by gx, right? And then we are going to get the approximation, and you can choose big values of n, okay, big values or big number, big amount of rectangle to get a good approximation. All right, and this is the Riemann sum. Okay, the addition that I said just now. Okay, depending on the number of n, number of rectangle that we want to use. Okay, and then here is what we call as the approximation, right? And of course, you have learned about the Riemann sum previously. You know what's going next, right? Because we believe that the approximation appear to become better and better as n approaches infinity. All right, so we have this limiting process. Okay, that is a equal to limit as n goes to infinity or delta x goes to 0, summation from I equal to 1 until n, fxi asterisk minus gxi asterisk times the base of the rectangle, that is delta x. So that is our a, okay, the area that we are going to get. Now we are adding one more term from the previous slide, that is we take the limit, right? Meaning that we are going to get the exact value. Okay, and of course this can be extended to the concept of definite integral that we talked previously. Okay, the limit that we have here we can extend. So this is similar to the Riemann sum definition that we have learned previously, and we extend the idea to definite integral. So it's the same thing here. Okay, we extend to definite integral of f minus g, and that brings us to this formula 2. So let's just go through the area A of the region bounded by the curve y equal to fx, y equal to gx, and the lines x equal to a, x equal to b, where f and g are continuous, and fx greater than or equal to gx for all x in AB is given by a equal to the integration from a to b fx minus gx dx. Right. So now, rather than using the Riemann sum to get the approximation, yeah, you can still do it, no problem. There are times, there are cases in real life that we might need to resort to that kind of approximation. That's okay. Okay, but if you are able to perform integration faster than that, so we always prefer to do the integration, and this is the formula for the integration. Right. Okay, so in the case where both f and g are positive, okay, the example that we used earlier is the more general one, where gx is a negative function, right? But now we have both f and g, they are both positive, all right? And you can see from this figure here, okay, what we are actually calculating, the area that's being bounded by f and g, still f always greater than or equal to g, all right? We are actually calculating area under the y equal to fx. Okay, if I'm going to draw, so it will be from here, everything. Okay, area under the y equal to fx actually being bounded by y equal to fx and y equal to 0. And then the second thing, okay, we just minus the area under y. I put this in different direction. Okay, this part. All right. Okay, so what left to us is the part that we have here. So I've just put some with doodling here so that you can differentiate between the curves that we are talking about, right? So we extend the idea that of that to the form that we are more familiar with, the integration itself, right? So we know that the area under y equal to fx above x-axis is given by integration from a to b fx dx, and the area under gx being bounded and above x-axis is given by integration from a to b gx dx. And then by using the properties of integration, okay, we have the formula that we had in this figure earlier. I'm sorry, this uh, for this result 2 here. Okay, that brings us to the formula for the definite integral. All right, so let's take a look at one example on how to perform the calculation. Okay, this is more related to your exam or your test. Right, we want to find the area of the region bounded above. Okay, it's being stated here, but in test it might not be stated above or below. You have to decide, okay, on your own. Find the area of the region bounded above by y equal to x squared plus 1, bounded below by y equal to x, and bounded on the sides by x equal to 0 and x equal to 1. So this is pretty straightforward. You are giving the lower bound, that is 0, the upper bound of the integration, that is x equal to 1, and then you know what function will be on top. Okay, that is x squared plus 1, and from below you have y equal to x, and now you just have to plug in into the formula, right? Okay, so what you are going to have is that a is equal to integration from 0 to 1, and then you have the first or the top function that will be x squared plus 1. Okay, and then the lower function, the below function will be minus x, and then you need to put dx. So maybe to avoid confusion, I put another layer of bracket here, and then from here I think is your routine. Okay, that is finding the integration lah, x squared minus x plus 1 dx. So you have the power rule for integration. So you are going to have x cubed over 3 minus x squared over 2 plus x, and then you have to plug in the values. Okay, of course you just have to plug in when x equal to 1, because when x equal to 0, all terms that we have inside here is also are zeros. All right, so this one I think you can do the calculation on your own, and then you'll get that the answer is 5 over 6. Okay, as easy as that. And the figure that we have at the side here is just to illustrate to you, okay, the rectangles, okay, that can be used for approximation, the origin of the definite integral, of course. All right. Okay. So next, okay, we want to see what are other possibilities. Okay, I would say possibilities. So we have here the same thing that we did earlier. Okay, so you can have the same thing that is from this figure. So we have the in this figure 4, right? So figure 4, you can see here we are given x equal to 0, x equal to 1. Okay, but in most of the case, we are not given. Okay, so this is one case. Okay, that remember the condition that we give is that fx greater than or equal to gx. Okay, but of course in this one possible case is that fx equal to gx, and that will be the case where we have it being bounded here. So if you try to extend this function, okay, you can have this red one until here, okay, until here, but that is not the case here because it's no longer being bounded, okay, not what you call being uh, within, okay, the function and the other bounds from the left and from the right here. Okay, so we can have this possible case, and if in this case a is not given, you have to find the point of intersection between fx. Okay, we consider the yt here actually is being denoted as y top, y bottom, right? So you have to find the point of intersection first, okay, before you can use the a. Okay, in this case you are not given the a. okay, you might be given by B, something like this being bounded above by YT, bounded below by YB, and then also bounded by X equal to B. Maybe B is equal to 2 to 3 and so on, but you're not given your A. Okay, you have to find your A by considering the point of intersection. That is, you have to equate the two function, that is fx equal to gx, for example. All right, and then you're going to now do some algebraic operation to get the value of x, and then you have to verify the value of x. Okay, this will be included in your problem sets lah, in your tutorial, so that you can practice the cases. I would say the more general case lah, okay, which many possibilities of having point of intersection, and it's also possible to have 2 point of intersection. Okay, that is from the left here for A and also for B, right? And then if that is the case, you are going to be given only bounded above by YT, bounded below by YB, nor A nor B in the problem. So by using this equality, you need to solve it. You are going to get two values of X. So you have to determine which one is A and which one is B. Okay. And also one other possible case is that you are not going to be given the location of the curve, either above or below. You'll be given bounded by YA, maybe not A lah, bounded by Y1, bounded by Y2, for example. Then you have to determine which one is the above function, which one is the below function. And you can get that from the point of intersection, and then within the interval, okay, you have to determine, you have to maybe plug in, substitute some values, and you are going to see which one is the top function, which one is the below function. All right. Okay, so this is just reiterating the thing that we did earlier, but this slide or this our textbook just try to make it more general. The area of a typical rectangle is given by YT minus YB, where we get the height of the rectangle. If you try to relate back to the Riemann sum, multiply with delta x, okay, the base of our rectangle, and that brings us to this one. Okay, if earlier we have yx minus dx, okay, yx asterisk minus dx asterisk, okay, but now we have, you know, something more general, y top, y bottom, okay, and using the definite integral notation, this is what we are going to have, okay, summarizing the procedure of adding every single rectangle n goes to infinity, okay, and then we are going to get the exact value of the area that is being bounded by two curves, okay, and of course by x equal to a from the left and x equal to b from the right, okay, to make sure that our integration got the limit. If not, then it is possible for it to not be bounded. Okay, imagine it is oscillating, right? Okay, it's not being bounded, technically not being bounded by every single direction. Okay, but if you have the case that we had earlier, okay, where it is a point of intersection, so it's being bounded in some sense lah. All right. Okay, so this is another example, okay, where we have several intersection points. All right. Okay, so I would assume that the question being given here is something like you are given your A and B, but then you are given two functions that could be oscillating, right? And you have to determine which part or which interval your function, your fx is on top, which function, which interval your fx on top, which interval your gx is on top. So in this case, for example, okay, so you have two functions, gx and fx, and you notice that for the first part, that is this interval, okay, a from maybe c, okay, I'm going to put d here. Okay, in this case, there are two intersection points, right? But then when you construct, okay, you have to determine the intersection point by having gx equal to fx, and then you try to solve this one, right? And then you get the intersection points, that is x equal to c and d, and then Okay, if I try to construct this properly, it will be you are going to have A given to you, and then C given to you. I'm sorry, C and D you get from this solving this equality, and then you have B given to you. And then for each interval that I said here, A to C, C to D, D to B, you have to determine which one is the top function. Okay, that is, for example, this one is 0 and 2, for example. All right, so you just try to plug in one value in between here. That is, for example, x equal to 1. Okay, you plug in into gx, you plug in x equal to 1 into fx, and you see which one is bigger and which one is smaller to determine which one is the top function, which one is the bottom function. And then you repeat the same process for this interval and also for this interval. And then in computing, okay, even though you have this piecewise function, but technically what you are doing is you find the first area, that is from here to here, you find the second area, you find the third area. So in this case, fx greater than gx, fx greater than gx, and for S2 here, gx is greater than fx. So that's why we have this piecewise function lah, indicating this modulus symbol here, indicating that we want the positive value. If gx is greater, then you need to flip the location. Okay, for example, gx greater than equal to fx, so we have gx minus fx inside our definite integral. All right, so the expressions for a that we had just now, okay, the combination, okay, the area between the curve y equal to fx and y equal to gx, and between x equal to a and x equal to b. Okay, notice the first thing that we discussed earlier, one of the condition is that fx greater than or equal to gx, but now it's missing. Okay, but we have the modulus symbol here, indicating that fx and gx can, changing their role as the top function, sometimes fx, sometimes gx. All right, so let's take a look at one example indicating the possible problems that you might have when not given the intersection point. That's one thing. And then another thing is the role of top and bottom function keep changing between the two function fx and gx. So two function given to us in this example, y equal to sine x, and then y equal to cos x. And then we have x equal to 0 and x equal to pi over 2. And most of the time, student might incline, okay, to possible, not always. Okay, we have 0 until pi over 2. And then some student, they straightforwardly, maybe they try some values that is, close to 0, for example, and then they are going to get that cos x is the top function. Maybe they tried some values here, okay, without looking for the intersection points. So the first thing that you need to do is find the intersection points, right? Because intersection point is defining which one is the top function, the interval wise, right? And also defining the limit. The limit can no longer be 0 until pi over 2. But this is what I'm highlighting here is one common mistake, okay, done by students. So we have integration from 0 to pi over 2. And then because the student tried some values that is closer to x equal to 0, so he or she thinks that cos x is the top function. So just take cos x minus sine x and then dx. The calculation will give some value, but of course the value is wrong, right? So the first thing when you are given this kind of problem is to determine the point of intersection, that is by equating sine x equal to cos x, right? You can solve it in any way that you prefer, right? And then you are going to get that the intersection, okay, occur when x is equal to pi over 4. Okay, without looking at this figure, okay, you can still get this value by equating sine x and cos x here. All right, and then like I said just now, you can, it's tedious, okay, but it you know remove the potential, okay, remove the probability of making mistake here. So you have here from 0, okay, and then you have pi over 2, and then you have the intersection point, that is pi over 4. And then you can try to plug in the values, or maybe you are good with the shape of the function. Okay, you can determine lah, or you can state in words that for the case of, or for the interval between 0 to pi over 4, you're going to get that cos x is greater than or equal to sine x. Okay, without looking at this figure, of course. Okay, but if you want to draw it, it's helpful for you. And then for the second interval from pi over 4 to pi over 2, okay, you are going to see that this case is inverse. Sine x is greater than or equal to cos x. Right, and then from here, without the figure again, you can construct the formula to find the area bounded by the curves and the value x equal to 0 and x equal to pi over 2. All right. So another thing that I need to highlight is that when solving this one, you are going to have infinite values of sine x. I'm sorry, infinite values of point of intersection. Okay. There are maybe sometimes you get, you have the period, right? But now the values that you have to choose must be between x equal to 0 and x equal to pi over 2. But if it is bigger, maybe I don't know, maybe some values bigger than pi over 2, it's possible to have two intersection points. Then you are going to have more intervals that need to be considered here. All right. So now constructing the formula for finding the area bounded. Okay, you are going to have the first interval that is from 0 to pi over 4. Okay, so this case here, this case here, that you are going to have cos x minus sine x dx. Okay, so that's for this particular interval. Okay, and then for the second interval, you are going to have integration from pi over 4 to pi over 2. All right, and then for this case, sine x is bigger. You have, put the square bracket, sine x minus cos x dx. Right, so I think finding the integral for cos x and sine x is easy for now. All right, and then you do the process, get all required workings, and then you will get that the answer is equal to 2 square root 2 minus 2. So that will be the answer for this example. All right, next. Okay, I think you have done this in the past, but maybe not not much discussion. You know how to perform it. That's good already. That's sufficient for your test and exam. But you have to know how it actually works. All right. Some regions are best treated by regarding x as a function of y. Right, so now we want to perform the integration with respect to y. If a region is bounded by curves with equation x equal to fy, x equal to gy, y equal to c, and y equal to d, meaning that you have an inverse of everything that we did earlier. We have y equal to fx and y equal to gx, right? Now we have x equal to fy, x equal to gy, and now c, okay, is in this form, all right, horizontally, right? Horizontal line, y equal to c and y equal to d. F and g are continuous, fy greater than or equal to gy, all right? And then we get this formula, all right, for the integration that is being done with respect to y, right? So in terms of approximation using rectangle, so you can refer to this figure where the delta y is now, now we are looking the rectangle in, what you call, you have transform it, okay? You have, sort of turning it like 90 degrees, all right? So you are considering the base is here now. If you want to consider as height, that is also possible, not a problem, because that is only perspective. But now the distance, okay, between the curve is being observed from this direction, right? So we have x equal to gy, x equal to fy, but you need to consider the rightmost function to be similar to the top function that we did earlier. Okay, so now we have fy, because that is the rightmost function, fy minus gy here, right? And then you get the same thing here. and then the value of C and D. It's nothing special with this. C and D, just not to make you confused with A and B, we use when performing integration with respect to X. So it's just a letter, right? Just C and D. So we have integration from C to D, Fy, the rightmost function, minus Gy, the leftmost function. Okay, and similar to integration with respect to X, it can be a function that is Gy could be here as well. If just now we have, okay, this function. Okay. Okay. So bounded by this one. So we have here is fx, here is gx. So it's also possible to have the same case for y. Okay. Doing integration with respect to y. So this could be our gy. This could be our fy. So that's not a problem. Okay. Because you are going to get the function to be uh, negative lah. Because now we are considering x, right? So x beyond the y axis here will give you negative value. So it's basically the same thing. It's just that we are twisting the axis for the integration with respect to x previously. Now we perform integration with respect to y. All right. So this is just making it more general. Just now we have top and bottom. So now we have right and left. Good. So right and left, top and bottom, they are just perspective. They're just later. So it's possible to have this case. So you can see we have here, okay, where you have to find the point of intersection between XR and XL. And then you solve here, okay, to get the point here. Okay, so that point, okay, the Y value will you be used as your D in the limit as the limit of the integration. Then the rest will be the same calculation. And don't worry much, okay, this kind of computation will also be included in your problem sets.